Welcome back to the Deep Dive. Today, we're not messing around. We're going straight for the heavyweights.
Oh, yeah, the big ones.
I'm talking about the two neurotransmitters that, they seem to dominate every single conversation about mental health, addiction, motivation, and just, frankly, how we all feel when we wake up in the morning. We are digging into Pharma 13.
It is a massive topic, and just to be precise for everyone, we're synthesizing Chapter 13 from Goodman and Gilman, which gives us that, deep molecular machinery, the nuts and bolts.
Real granular stuff.
The really granular stuff. And we're combining it with Chapters 16, 28, and 29 from Katzung, which kind of gives us the clinical scaffolding, puts it all in context.
And the topic, of course, is serotonin and dopamine.
Correct. But before we even start, I think we have a mission today. We really need to dismantle the pop culture labels that have just been slapped onto these molecules.
You mean the idea that serotonin is the happy chemical and dopamine is the pleasure chemical?
Mm.
Because that's pretty much all I see. It's on T-shirts, it's on coffee mugs.
It's everywhere. And it's a comforting idea, right? Oh, I'm sad, I just need more happy chemical. But while there's maybe a tiny grain of truth there, it's so reductive, it's actually dangerous.
So.
It's like saying the internet is just for sending emails. I mean, yeah, it does that, but you're missing the entire universe of function. If you actually look at the source material, these aren't just happy or sad switches. They are systems of context.
Context. What do you mean by that?
They regulate everything from, say, vomiting and blood clotting all the way up to voluntary movement, hallucination, and even deep belief systems.
It's just wild to think that the same chemical that makes you feel that, yes, that sense of reward is also the one responsible for making you throw up.
Yeah.
Or controlling whether your hands shake when you reach for a cup of coffee.
That is the beauty and, frankly, the terror of pharmacology. So today, we're going to build a conceptual map of these systems. We're not just going to sit here and memorize drug names.
No flashcards today.
No flashcards. We want to understand the architecture. We're going to see how Katzung uses these drugs to treat things like Parkinson's, schizophrenia, depression, but we're going to view all of that through the lens of Goodman and Gilman's molecular reasoning.
The receptor subtypes, the G-protein coupling.
The precise machinery of the synapse, exactly. We're not just driving the car today, we're stripping the engine down to the pistons.
Okay, I like that. And I assume the usual disclaimer applies.
Absolutely. Just a quick reminder for everyone listening, this is an interpretive synthesis to help with your revision. It is not and can never be a substitute for reading the textbooks.
You still have to do the reading.
You absolutely still have to do the reading. Katzung and Goodman and Gilman are the primary sources. Think of us as just the study guide.
Okay, let's unpack this. We have a lot of ground to cover, so where do we start?
I think we need a roadmap. There are 4 key takeaways I want you to hold on to as we go through this. Keep them in your head. First is distributed signaling.
Distributed signaling.
You have to understand why the same chemical can cause nausea in the gut and hallucinations in the brain. It's all about location, location, location.
Real estate matters.
Precisely. Second is receptor diversity as destiny. The molecule dopamine or serotonin, it's just a key. The lock, which is the specific receptor subtype.
Like 5-HT1 versus 5-HT2 or D1 versus D2.
Exactly. The lock determines what happens when that door opens. It's destiny.
So the chemical is the same, but the reaction depends entirely on who's receiving the message.
Yes. It's like having one key that opens the library door and another door to the boiler room. Same key, very different outcomes.
Okay, what's third?
Third is the concept of tone versus spikes. We have to distinguish between the constant background signaling, which we call tone, and these sudden, sharp bursts of release, which are phasic.
And drugs affect those differently.
Very differently. And finally, number 4, trade-offs. This is really the clinical heart of the episode. We need to understand why treating a movement disorder can cause psychiatric side effects, and why treating a psychiatric disorder can cause movement problems.
That interconnectedness is something I'm really excited to get into. It feels like you can't touch one thread without the whole web shaking.
That's a perfect analogy.
But let's start at the very beginning. The raw materials. Where do these chemicals actually come from in the body?
Let's do it. Segment 1, molecular origin, synthesis, and termination. Let's start with serotonin, or, to be proper, 5-hydroxytryptamine, 5-HT.
So if we're building this from scratch, what's the raw material? The body doesn't just conjure these chemicals out of thin air.
It starts with an amino acid, tryptophan. You get this from your diet, turkey, cheese, nuts, that sort of thing. Tryptophan is then actively transported into the brain.
But just eating more turkey won't make you happier, right?
Right, because there's a bottleneck. The magic happens with an enzyme called tryptophan hydroxylase, or TPH. This is the rate-limiting step.
I always hear that term rate limiting. What does that actually mean for the system in practical terms?
Think of it like an assembly line making cars. You can have 1,000 tires and 1,000 steering wheels stacked up, but if you only have one person installing the engines and they work at a set speed,
You're only getting 1 car an hour.
you're only getting 1 car an hour. TPH is the engine installer. It's the bottleneck. The entire speed of serotonin production is determined almost entirely by how active this one enzyme is.
So if TPH slows down for some reason, the whole supply chain just grinds to a halt.
Exactly. So the pathway goes from tryptophan, TPH makes it into 5-hydroxytryptophan, and then another enzyme snips off a carboxyl group, and boom, you have 5-hydroxytryptamine, serotonin.
Simple enough.
But here's a fascinating connection that Goodman and Gilman points out. In one very specific part of the brain, the pineal gland, this pathway doesn't stop at serotonin.
It keeps going.
It does. Serotonin actually acts as a precursor. The pineal gland takes serotonin and, through a couple of steps, it acetylates it, then methylates it to create melatonin.
The sleep hormone. So serotonin is literally the raw material for regulating our sleep-wake cycle.
In a sense, yes. And Goodman and Gilman has this lovely, almost poetic phrase for it. They note that melatonin regulates circadian rhythms in sleep, and in that regard, it could be thought of as a pigment of the imagination.
A pigment of the imagination. That is surprisingly beautiful for a pharmacology textbook.
It is, isn't it? And it's also a nod to the chemistry. Melatonin is chemically related to pigments, which, funnily enough, brings us to our other heavyweight, dopamine.
Okay, let's switch lanes. What's the raw material for dopamine?
Dopamine is synthesized from another amino acid, tyrosine. The pathway goes from tyrosine to dopa and then to dopamine. But here's that pigment link I mentioned. Dopamine is very closely related to melanin.
Wait, you mean the actual melanin that gives skin its color? The stuff that gives you a tan?
The very same family of molecules. And in fact, there is a specific area in the brainstem called the substantia nigra.
Which translates to black substance.
Correct. And have you ever wondered why it's called that? Why it's black?
I just assumed it was, dark tissue.
It is dark because of neuromelanin. Neuromelanin is a byproduct of dopamine synthesis that accumulates in those specific neurons. It is a direct, visible marker of dopamine production.
So you can actually see it.
Oh, yeah. If you look at a healthy brain slice, there's this distinct black stripe in the midbrain. But when those cells die, as they do in Parkinson's disease, the black substance literally fades away.
So you can see the disease with your naked eye.
You can see the loss of pigment. It's chilling. It's like the color literally grains out of that part of the brain as the disease progresses.
That is a haunting image. Okay, so we've made the chemicals. We have serotonin and dopamine floating in the synapse. But a signal isn't useful if it just lasts forever. You have to be able to turn it off.
Termination is just as important as synthesis, maybe more so. Imagine if your keyboard key got stuck every time you pressed A. You couldn't type anything else. The synapse has to be cleaned up and fast to be ready for the next signal.
And there are 2 ways to do this.
2 main ways. You have the vacuum cleaners and you have the breakdown crew.
Let's talk vacuums first. This is reuptake, right?
Yes. These are the reuptake transporters. They are proteins that sit on the presynaptic neuron, the sender, and they physically suck the neurotransmitter back inside to be recycled or broken down.
So for serotonin, it's SERT.
SERT, the serotonin transporter. And for dopamine, it's DET, the dopamine transporter.
And these are probably 2 of the most famous drug targets in all of medicine.
Absolutely. SERT is the target of SSRIs, the selective serotonin reuptake inhibitors, which we use for depression. And SSRI effectively jams the vacuum cleaner's hose.
So serotonin stays in the synapse longer, amplifying the signal.
It forces the signal to linger.
Yeah.
Exactly. But SERT is also a major target for cocaine.
And cocaine hits both, doesn't it? It hits SERT and DAY.
It does. Cocaine acts as a simple plug. It just blocks both SERT and DAY. It clogs the vacuum cleaners for both the mood system and the pleasure and movement system. This leads to that massive, chaotic flood of neurotransmitters because they have nowhere to go.
Okay, so that's the vacuum. What about the breakdown crew? The enzymes.
So once the chemical is back inside the neuron, or even while it's floating around, it can be metabolized, chewed up. The main enzyme for both is MAO monoamine oxidase.
And we have drugs that stop that too, the MAO inhibitors.
Yes, the MAOIs. They were actually the very first antidepressants ever discovered. By stopping the breakdown, you increase the overall supply of the neurotransmitter.
Makes sense.
There's also a second enzyme that's more specific to dopamine and other catecholamines. It's called QOMT, catecholomethyltransferase.
KOMT. That one always sounds like some kind of intense military acronym to me.
It effectively acts like one in the synapse. It's another way to break down dopamine. And we'll see later why blocking COMT becomes a really important strategy in treating Parkinson's.
Okay, but before we leave this molecular part, you mentioned there's a clinical marker, CAT-some highlights, that ties this all together.
Yes. It's a nice little diagnostic pearl. When serotonin is broken down by MAO, it turns into a metabolite called 5-HIAA. And this is eventually excreted in the urine.
And why do we care about a waste product in the urine?
Because it's a window into the body's total serotonin production. It's crucial for diagnosing something called carcinoid tumors. These are rare tumors of those enterochromaffin cells in the gut.
The ones that make most of our serotonin.
Right. And these tumors can act like runaway serotonin factories, just pumping out massive amounts of it. So if a patient comes in with this weird constellation of symptoms, unexplained flushing, diarrhea, heart valve problems, you check their urine for 5-HIA. If it's sky high, it's a huge clue that there's a serotonin factory running overtime somewhere in their body.
That is a perfect segue, actually. You mentioned the gut. I think most people, if you ask them on the street, would say serotonin is a brain chemical. They'd point to their head. But the sources say that's barely the tip of the iceberg.
It is a massive misconception. So let's move to segment 2. Serotonin, the messy architect. If you actually look at the distribution, a staggering 90% of the body's serotonin is not in the brain. It's in the gut.
90%. So my happy chemical is mostly managing my digestion.
Essentially, yes. The gut is often called the second brain, and serotonin is its primary signaling molecule. It regulates GI motility, how fast food moves through you. It's the master controller of your intestines.
This explains so much about the side effects of antidepressants.
Yeah.
I've read that the number one reason people quit SSRIs in the first few weeks is the GI issues.
It's the classic pharmacological tax. You swallow a pill, say an SSRI, because you want to change your mood, which is happening in your brain. But the drug has to pass through the gut first. And the gut is just lined with serotonin receptors.
So the drug just screams activate at everything.
It screams activate, and the gut responds with eject. That leads to nausea, diarrhea, cramping. You're effectively overstimulating the digestive system's motility controller.
That makes perfect sense now. But it's also in the blood, right? I remember reading something about platelets.
It is, but here's a little trick question. Do platelets make their own serotonin?
No. I remember Goodman and Gilman being very specific about this. They don't have the enzymes. They lack TPH.
Correct. Platelets cannot synthesize serotonin, but they are packed full of it. They act like little thieves or maybe sponges. As they circulate through the blood vessels of the gut, they use that SERT transporter, the vacuum, to suck up serotonin from the gut circulation and store it in these dense granules.
But why? Why do platelets need a secret stash of stolen serotonin?
For hemostasis, for stopping bleeding. Imagine you get a cut, a blood vessel is injured. Platelets rush to the scene. When they hit that damaged endothelium, they activate and they release their stolen stash of serotonin right at the site of injury.
And what does the serotonin do there?
2 crucial things. First, it's a powerful vasoconstrictor. It tells the smooth muscle around the blood vessel to clamp down, to squeeze shut and stop the bleeding. Second, it acts as a signal for other platelets to come and aggregate, helping them stick together to form a clot.
So serotonin is literally saving us from bleeding out. It's a localized tourniquet and a call for backup.
It's all about context, right? In the brain, it's mood. In the gut, it's movement. In the blood, it's a plug.
Okay, so let's finally get to the brain. Let's talk about the Raphe nuclei.
The Raphe nuclei. This is the headquarters for serotonin in the brain. It's a cluster of nuclei deep in the brainstem. But what's really remarkable is their projection. They send axons to literally every part of the brain and spinal cord.
Every single part.
Every part. Goodman and Gilman describes it almost like a sprinkler system, or what's called volume transmission. It's not just point-to-point wiring like a telephone line. It's more like it's bathing the entire brain in serotonin to set the general tone of neural activity.
It's the background hum of the brain.
Exactly. But to understand the specific effects, the specific notes it plays, we have to enter what I call the receptor maze. Goodman and Gilman identifies at least 14 distinct subtypes of 5-HT receptors.
14. That seems absurdly complex. Why would nature need so many different locks for the exact same key?
Because evolution is brilliant. It allows one molecule to do many different and sometimes completely opposite things. If you only had one receptor, Serotonin could only ever do one thing. With 14, it can be excitatory here, inhibitory there, fast here, slow there.
It's incredible flexibility.
It's total flexibility. We can group them into three main families for our purposes today: the 5-HT1 family, the 5-HT2 family, and the oddball 5-HT3.
Okay, let's break them down. 5-HT1. I think of these as the quiet receptors.
That's a great way to think of them. They are guy-coupled, which means they inhibit an enzyme called adenyl cyclase, which decreases cyclic AMP. The bottom line is they generally inhibit neuronal firing. They quiet things down.
And they're often found as autoreceptors, right? On the presynaptic neuron itself.
Exactly. They act as a feedback brake. They tell the neuron, okay, that's enough serotonin in the synapse. You can stop releasing it now.
And this is where migraine drugs work.
Yes. This is a huge clinical application. Migraines are complex, but a key part of the pathology involves the painful vasodilation of cranial blood vessels. They swell up and throb. The triptan drugs, like sumatriptan, are 5-HT1D and 5-HT1B agonists.
So they stimulate these quiet receptors.
Specifically on those blood vessels, they cause vasoconstriction, they clamp down on that throbbing vessel, and they also quiet the nerve transmission of pain signals.
So 5-HT1 is quiet and strict. What about 5-HT2? The opposite.
Pretty much the opposite. 5-HT2 is the loud receptor. It's GQ coupled. It works by increasing cellular activity through releasing intracellular calcium. It causes things like smooth muscle contraction in the gut and bronchi and platelet aggregation.
But in the brain, 5-HT2 gets really interesting. This is where things get trippy.
It gets psychedelic.
Yeah.
The 5-HT2A receptor subtype is the primary target for hallucinogens like LSD, psilocybin from magic mushrooms, and mescaline. LSD acts as a partial agonist at this specific receptor.
It pushes the psychedelic button.
It pushes the psychedelic button. It disrupts normal sensory filtering, leading to sensory overload and altered perceptions.
So if 5-HT1 is saying, shh, quiet down, 5-HT2A is screaming, look at all the colors the walls are breathing.
That's a pretty good summary. It breaks the brain's filter, and as a consequence, many of the newer atypical antipsychotics work by blocking this very receptor to help stop hallucinations. We'll get to that.
A very cool symmetry there. And then we have the oddball, 5-HT3.
5-HT3. It's the odd one out because it is the only one that is not a G protein-coupled receptor. It's a ligand-gated ion channel.
Meaning it's fast. No second messengers, just open the gate.
Incredibly fast. A direct, immediate depolarization of the cell. And where do we find a very high density of these 5-HT3 receptors? In a place called the chemoreceptor trigger zone, or CTZ, in the brainstem.
The vomit center.
The vomit center. Evolutionarily, this is a poison detector. If you eat something toxic, serotonin spikes in your gut. That signal travels up the vagus nerve. It hits these fast 5-HT3 receptors in the brainstem, and the brain's immediate response is eject.
So that immediate, overwhelming urge to vomit is serotonin hitting a fast channel.
Exactly. And this is why we use drugs like ondansetron, which you might know is Zofran. It's a 5-HT3 antagonist. It blocks that fast signal. It's a miracle drug for chemotherapy patients because many chemo drugs are toxic and trigger that massive serotonin release.
It really is. So to summarize the families, we have quiet, 5-HT1, loud psychedelic, 5-HT2, and vomit, 5-HT3.
A very functional, if slightly crude, simplification. But it works. And just to show how complex this all gets in a living system, Katzum describes the triphasic response when you inject serotonin intravenously in an animal model.
Oh, this was the blood pressure roller coaster. It was wild.
Right. Imagine you just inject a bolus of 5-HT directly into a vein. What happens to blood pressure? First, it drops. It drops rapidly. Why? Because heart rate slows down via something called the Bisolgerish reflex, a chemoreceptor reflex.
The body senses a chemical shock and pulls the emergency brake.
Exactly. Then, phase 2. Blood pressure shoots up, often higher than baseline. That's the 5-HT2 receptors on blood vessels all over the body getting hit and causing widespread vasoconstriction.
And then it falls again?
And then phase 3, it drops again to a prolonged low level. This is due to vasodilation in the blood vessels of skeletal muscle.
Down, up, down. It's a complete mess.
It is a mess. And it shows you that the net effect of serotonin isn't one thing. It's a constant tug of war between different receptor populations in different tissues. And if you have way too much serotonin everywhere all at once, you get serotonin syndrome.
This is a true medical emergency.
Absolute emergency. It often happens when people are taking multiple serotonergic drugs, like mixing an MAO inhibitor with an SSRI. You've stopped the breakdown, AND blocked the reuptake, the synapse just floods.
And what does that look like in a patient?
It's a triad of symptoms, cognitive changes like confusion and agitation, autonomic instability fever, sweating, wild swings in blood pressure, and neuromuscular hyperactivity.
The neuromuscular part is interesting.
It is. You get tremor, clonus, and hyperreflexia. The patient becomes rigid and shakes uncontrollably. It's those 5-HT2 receptors on skeletal muscle being hammered. It really highlights that serotonin isn't just a mood chemical, it's a fundamental neuromuscular regulator too.
Which brings us very nicely to the master of movement, dopamine. Let's get into segment 3.
Dopamine, the engine of motion and reward.
If serotonin is like a sprinkler system, sort of bathing everything, dopamine seems more like a set of specific, targeted highways.
That is the perfect analogy. Dopamine is fundamentally defined by its pathways. It's not a general broadcast, it's a specific transmission along very well-defined lines. And for our purposes, we need to know 4 major highways. I like to think of them almost as 4 different personalities of dopamine.
Okay, lay them on me. Highway 1.
The nigrostriatal pathway. From the substantia nigra to the striatum, this is the drill sergeant.
The drill sergeant. Why that?
Because it demands order. It controls voluntary movement. It ensures your movements are crisp, initiated when you want them, and stopped when you want them. When the drill sergeant goes on leave, when these neurons die, you get Parkinson's disease. You lose that crisp control.
Okay, drill sergeant for movement. Highway 2.
The mesolimbic pathway. From the ventral tegmental area, or VTA, to the nucleus accumbens. This is the party animal.
The famous reward pathway.
It is, but reward is a little too simple. A better word is salience. It tells your brain what is important in the environment. It drives motivation and, of course, addiction. It's the part of your brain that says, that thing, that was important, do it again.
And when the party animal gets too loud.
You get the positive symptoms of schizophrenia, hallucinations, delusions. The brain starts assigning profound meaning to things that have no meaning.
Okay, highway 3. The mesocortical pathway.
From the VTA up to the prefrontal cortex. This is the accountant.
The thinking, planning part of the brain.
Cognition, executive function, working memory, motivation. And interestingly, while too much dopamine in the party animal pathway causes hallucinations, too little dopamine in this accountant pathway is thought to cause the negative symptoms of schizophrenia.
Like apathy, social withdrawal, inability to plan.
Exactly. So in one disease, one pathway is screaming and the other is silent. It's a disease of dysregulation.
And finally, highway 4.
The tuberoinfundibular pathway. It's a short one, from the hypothalamus down to the pituitary gland. This is the nanny.
The nanny. Why the nanny?
Because it controls milk production. Dopamine in this pathway acts as a constant tonic brake on the hormone prolactin.
Prolactin being the hormone for lactation.
Correct. So normally dopamine is always saying no milk right now, but what happens if you block dopamine, say, with an antipsychotic drug?
You take the brakes off prolactin.
You lock the nanny in the closet, prolactin levels spike,
Yeah.
and you can get a side effect called galactorrhea, which is inappropriate milk production in men or in non-pregnant women.
That is a very specific and I imagine very distressing side effect.
It is the perfect example of the clinical disconnect. We want to treat one pathway, but our drugs are rarely that specific. They often hit all of them.
So you try to evict the party animal in the mesolimbic system.
And you end up firing the drill sergeant and the nigrostriatal system and locking up the nanny and the tuberoinfundibular system.
It's a blunt instrument problem.
It is. And just like serotonin, the receptors matter immensely. We can simplify them into 2 families. The D1-like family, which includes D1 and D5 receptors. They are Gs-coupled, they turn things on, they're the gas.
And the other family must be the brake.
The D2-like family, which includes D2, D3, and D4, they are G-coupled, they turn things off, they're the brake. And the D2 receptor in particular is the main target for almost all antipsychotic drugs and many anti-Parkinson's drugs.
Okay, let's apply this map. Let's move into the clinic. Segment 4, Parkinson's disease. A case study in motion.
Parkinson's is the classic example of a specific pathway degenerating. You are losing those dopamine-producing neurons in the nigrostriatal pathway.
As the black pigment fades from the substantia nigra, the drill sergeant is gone.
He's gone. And Katsung helps us visualize the circuit here. Normally in the striatum, there's a delicate balance between dopamine and another neurotransmitter, acetylcholine. Think of it like a seesaw. Dopamine on one side, acetylcholine on the other.
And what are their roles?
Dopamine promotes smooth, controlled movement. Acetylcholine promotes muscle tone and rigidity. They oppose each other. In a healthy person, the seesaw is balanced.
But in Parkinson's, you lose dopamine, so the acetylcholine side of the seesaw just slams to the ground.
Exactly. The cholinergic influence runs wild, completely unopposed, and the system locks up. You get the classic triad, rigidity, tremor at rest, and bradykinesia slowed movement.
There's a story in Goodman and Gilman that I found absolutely captivating. It reads like a true crime novel, the story of the frozen addicts.
This is one of the most tragic but scientifically important moments in the history of neurology. It's July 1982, Santa Clara County, California. Emergency rooms start seeing these bizarre cases, young people in their 20s and 30s, and they are completely immobile, frozen.
Like statues.
Like statues. They couldn't speak, couldn't move a muscle. They looked exactly like they had end-stage Parkinson's disease, but that's a disease that takes decades to develop. These people were young and healthy just days before.
The doctors must have been completely baffled. Was it a new virus? Some kind of mass hysteria?
That's what they thought. But one sharp neurologist, Dr. William Langston, noticed they were all heroin users, and they had all purchased a new synthetic designer heroin from the same street chemist.
And the chemist messed up.
He messed up badly. He was trying to synthesize a drug called MPPP, which is a potent opioid, but he was sloppy, he cooked it too hot or let the reaction run too long, and he accidentally created a contaminant called MPTP.
And MPTP is the neurotoxin.
It's actually a protoxin. MPTP itself isn't the killer. It crosses the blood-brain barrier very easily because it's lipophilic, it loves fat. Once it's inside the brain, an enzyme in glial cells, MAOB, converts it into its toxic form, MPP plus STEM.
And MPP plus is the assassin.
It's a molecular guided missile. The chemical structure of MPP plus looks just enough like dopamine that the date transporter, that vacuum cleaner we talked about, recognizes it and sucks it up.
But it only sucks it into dopamine neurons.
It's a selective uptake mechanism. It targets the very cells it mimics, and once it's inside, it goes straight to the mitochondria, the cell's power plants, and destroys them. The cell can't make energy, and it dies.
So these kids, in a matter of days, just wiped out their entire hygrostriatal pathway.
Instantly and permanently. But this awful tragedy had a silver lining. It proved unequivocally the dopaminergic link to Parkinson's, and it gave researchers a perfect animal model to test new drugs.
So how do we treat it? If they're missing dopamine, why not just give them a dopamine pill? It seems like the most obvious solution.
It does, doesn't it? Just replace what's missing. But the brain is a fortress. It is protected by the blood-brain barrier, the BBB.
The wall.
The wall. And dopamine is a polar molecule. It has a charge. The BBB is a lipid layer. It's fatty. Oil and water don't mix. If you inject dopamine into the blood, it gets to the BBB and just bounces off. It cannot get in.
So we need a way to sneak it past the guards. We need a Trojan horse.
Enter levodopa, or L-dopa. L-dopa is the direct precursor to dopamine. And critically, it looks like an amino acid. It has a passport. It can hitch a ride on the amino acid transporters to get ferried right through the BBB.
So it sneaks in disguised as food.
Exactly. Once it's safely inside the brain, an enzyme called dopa decarboxylase converts it into dopamine right where we need it. Problem solved.
But wait, Katsung is very clear that we never give L-dopa by itself. It's always combined with another drug. Why is that?
Because that enzyme, dopa decarboxylase, is not just in the brain, it's all over your body, especially in your gut and your blood.
So if I take an L-dopa pill by itself,
about 99% of it will get converted to dopamine before it ever reaches the brain, in the periphery.
And having a ton of dopamine floating around in your blood is bad news.
It's terrible news. It hits dopamine receptors in your heart, causing arrhythmias. It hits the chemoreceptor trigger zone, that vomit center, causing projectile vomiting. And now that it's been converted to dopamine, it can't cross the BBB anymore. So you have a patient who is vomiting, their heart is racing, and their brain still has no dopamine.
It's the worst of all worlds. So we need a bodyguard for the Trojan horse.
We need a bodyguard, and that bodyguard is carbidopa. Carbidopa is an inhibitor of dopa decarboxylase.
But hold on, if it inhibits the enzyme that turns L-dopa into dopamine, won't that stop the drug from working in the brain too?
That is the absolute genius of the pharmacology. Carbidopa is a polar molecule. It cannot cross the blood-brain barrier. It only works in the periphery.
Oh, that is so smart.
It's beautiful, isn't it? Carbidopa sacrifices itself. It shuts down the enzyme in the body, protecting the L-dopa so it can travel safely to the brain. Once L-dopa crosses that wall, it leaves carbidopa behind. Inside the brain, the enzyme is still active and it converts the L-dopa to dopamine right where we need it.
That is such an elegant piece of chemical engineering. Carbidopa holds off the attackers outside the castle walls so the king can get inside safely.
It's the absolute gold standard of treatment. But we also use other helpers. Remember the breakdown crew, COMT and MAO?
Right.
We can add a COMT inhibitor like entacapone, which also works in the periphery to prevent L-DOPA breakdown. Or we can use an MAOB inhibitor like selegiline, which works inside the brain to stop the newly formed dopamine from being broken down too quickly.
It's a multi-pronged strategy.
It's all about maximizing the signal, but there's one more class of drugs here, the dopamine agonists. These just mimic dopamine directly.
Like prenopexole and ropinirole.
Exactly. They don't need to be converted. They look enough like dopamine to stimulate the receptors, mostly the D2 and D3 receptors directly.
But they have this really weird and troubling side effect profile. I was reading about this. Patients developing, like, gambling addictions out of nowhere.
Yes. Impulse control disorders. It's a major problem. Because these drugs aren't regulated like natural dopamine, they don't come in little pulses with a signal. They provide a constant, unrelenting stimulation, and they hit the D3 receptors in the mesolimbic reward system.
The party animal pathway.
Yeah, they hit the party animal pathway hard. So you're trying to treat the tremor in the drill sergeant pathway, but you accidentally hyperstimulate the reward center.
And the brain just seeks out reward.
Compulsively. Patients with no history of it might suddenly blow their life savings at a casino or develop hypersexuality or compulsive shopping. It is the perfect, tragic example of a pharmacological trade-off. You're fixing the motion pathway, but you're destabilizing the meaning pathway.
Which leads us directly to the opposite problem. Not too little dopamine, but too much.
Yeah.
Segment 5. Schizophrenia.
Or, as we framed it, meaning and perception. The classic dopamine hypothesis of schizophrenia suggests that the positive symptoms, the hallucinations, the delusions, are caused by excess dopamine activity in that mesolimbic pathway.
So the party animal is trashing the house. The brain is assigning too much salience to things. A random noise isn't just a noise, it's a secret message from the CIA. A shadow isn't just a shadow, it's a demon.
Exactly. The brain's filter is completely gone. So logically, the treatment was to block dopamine. The first generation or typical antipsychotics like haloperidol are very strong D2 antagonists. They just clamp down hard on those receptors.
And they do work for the psychosis.
They do. They quiet the noise, but you can guess the problem. Remember the trade-offs.
The drug goes everywhere.
It goes everywhere. If you block D2 in the mesolimbic system, you help the hallucinations, but that drug also goes to the negrestriatal pathway and blocks D2 there.
And you shut down the drill sergeant.
And you cause Parkinson's symptoms. We call them extrapyramidal symptoms, or EPS. You get stiffness, tremors, a shuffling gait, a mask-like face. You are essentially chemically inducing Parkinsonism to treat psychosis.
That sounds like a terrible choice to have to make. Sanity or movement?
It was the central dilemma of psychiatry for decades. Do you want to be psychotic or do you want to be frozen? It was awful. Until the serotonin twist.
The atypical revolution. Drugs like clozapine, risperidone, olanzapine.
They're called atypical because they have a much lower risk of causing those terrible movement side effects. But for a long time, no one really knew why they were better.
And it has to do with serotonin.
It has everything to do with serotonin. Their defining feature is that they are strong 5-HT2A antagonists.
The loud psychedelic receptor we talked about earlier.
That very one. Now, you need to visualize this carefully because it's a bit of a brain twister. In the nigrostriatal pathway, the movement pathway, serotonin normally acts as a brake on dopamine release.
Wait, say that again? Serotonin usually stops dopamine release there.
Think of a 5-HT2A receptor sitting on a dopamine neuron like a parking brake. When serotonin hits it, the brake is pulled. Less dopamine comes out.
Okay, I think I follow. So, if I give an atypical drug that blocks that 5-HT2A receptor,
you are cutting the brake cable. The parking brake on dopamine release is released, and dopamine is now free to flow again in that specific pathway.
Whoa, so the drug blocks dopamine directly at the D2 receptor, but it unblocks it indirectly by acting on the 5-HT2A receptor.
Precisely. It's like having your foot on the brake and the gas at the same time. The D2 blockade says stop, but the 5-HT2A blockade says go a little bit. The net result in the movement pathway is that you have enough dopamine to move normally, preventing Parkinsonism. Because the drug still blocks D2 strongly in the mesolimbic system, you still get the antipsychotic effect.
That is it's incredibly sophisticated.
Yeah.
It's using one neurotransmitter system to fine-tune another.
It proves that these aren't isolated buckets of chemicals in the brain. They are deeply interconnected, interacting gears. You adjust serotonin to save dopamine.
Let's talk about when those gears get completely hijacked and ground down. Segment 6. Drugs of abuse and the transporter war.
This is where we really see that difference between tone and spikes.
We talked about the vacuum cleaners, DAT and CERT. This is where the war is fought. Let's start with cocaine.
Cocaine is a simple hijacker. It binds to the DAT and SUT proteins and just sits there. It physically blocks the vacuum's hose.
So dopamine and serotonin flood the synapse because they can't get taken back up. They can't go home.
Right. It's what we call a non-transported antagonist. But amphetamines are much more devious. They're what we call substrates.
What's the difference?
A substrate is something the transporter is tricked into carrying. Amphetamine looks enough like dopamine that the DAT transporter actually picks it up and carries it into the neuron. It's another Trojan horse, but this one has malicious intent.
What does it do once it's inside?
It creates total chaos. First, it gets into the synaptic vesicles, the little bubbles where dopamine is safely stored, and it kicks the dopamine out into the cytoplasm of the cell.
So you have all this raw, unpackaged dopamine just sloshing around inside the neuron.
Exactly. The concentration of free dopamine inside the cell gets massive. Then, and this is the real kicker, it forces the DAT transporter to run in reverse.
It turns the vacuum cleaner into a leaf blower.
The perfect analogy. It turns the vacuum into a pump, spewing all that leaked dopamine out into the synapse, completely independent of whether the neuron is even firing. It is a non-stop, artificial flood.
And how massive is that flood compared to, say, a natural reward?
Orders of magnitude higher. It's a tsunami compared to a pleasant wave at the beach. It's an unnatural, overwhelming spike.
And what is the brain's reaction to that kind of overwhelming signal?
Downregulation. The brain basically says, this is way too loud, I'm going deaf. And it starts to protect itself. It literally pulls the dopamine receptors off the surface of the postsynaptic cell and internalizes them.
It's turning down the volume.
It's turning down the volume. This is tolerance. And it means the baseline tone of the system drops. So when the drug wears off, your natural rewards, food, sex, social interaction, can't produce enough of a signal to feel good anymore. Things feel flat, gray, and hedonic. You now need the drug just to feel normal.
That's the trap. The spike destroys the tone.
It's a devastating neurobiological trap, and it brings us right back to the start.
The outro. We've navigated through migraines, depression, Parkinson's, schizophrenia, and addiction. And at the core of it all, it's just two molecules.
Two molecules, but playing out in infinite contexts. If I had to synthesize the whole thing down, I'd say serotonin is the great stabilizer. It's the context setter. It dampens sensory overload, which is why a drug like LSD, which messes with it, breaks that filter. Dopamine is the driver. It's the motivator, the reward seeker, the initiator of movement.
And the big lesson, the one that applies to all of pharmacology really, is the trade-off.
Always. You cannot touch one part of this intricate web without vibrating the whole thing. Treating a tremor might cause a gambling addiction. Treating a hallucination might cause a tremor. There is no free lunch.
So for the listener, the challenge is this. The next time you're reading Katsung or Goodman and Gilman, don't just memorize the name of the drug class.
Please don't. Visualize the receptor. Ask yourself, is this a D2 blockade? Where does that D2 receptor live? Is it in the striatum or the mesolimbic pathway or the pituitary? That kind of spatial systems level thinking is what turns a student into a clinician.
Pharma 13. It's an absolute beast of a topic, but I feel like we have a pretty good map now.
We have a map. Now you just have to go walk the territory, get back to the books.
Thanks for diving in with us today.
My pleasure. It was fun.
We'll see you on the next deep dive.